Early March 1945. The waters off Okinawa. Lieutenant Vernon Tebo's TBM Avenger from Escort Carrier Squadron 97 descended toward the churning Pacific, its right wing trailing smoke from Japanese anti-aircraft fire. The massive torpedo bomber, bearing Bureau No. 68767, carried a full combat load, one Mark 13 torpedo, nestled in its bomb bay, 2,000 pounds of destructive capacity, suspended beneath a single Wright R-2600 engine that continued turning despite the damage. Tebo fought the controls as his radioman Warren Lloyd called out altitude readings from the greenhouse canopy behind him. Ordnanceman Robert Tuggle manned the ventral gun position, scanning for enemy fighters. The Avenger shuddered, its engine coughing black smoke. At 1,100 feet, Tebo made his decision. They would not make it back to the USS Makassar Strait. The torpedo would have to go. The massive weapon dropped free, plunging toward the sea. Lightened, the Avenger gained precious altitude, but it was not enough. The engine seized. The propeller windmilled uselessly. At 700 feet, Tebo gave the order to bail out. 3 parachutes blossomed against the grey Pacific sky as the uncrewed bomber nosed down toward Ishigaki Island's coastal waters. Japanese patrol boats were already converging on the floating wreckage as the 3 aviators splashed down. Within hours, salvage teams would begin the laborious work of recovering what remained of the aircraft. What they would discover would fundamentally challenge their understanding of American manufacturing capability and strategic thinking about industrial warfare. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. The Grumman TBM Avenger represented more than military hardware. It embodied an entire philosophy of design that prioritized payload capacity, structural durability, and manufacturing efficiency over elegance or speed. Over the coming weeks, Japanese engineers would systematically examine this recovered bomber, documenting every aspect of its construction. The conclusions they reached would prove devastating to Japanese confidence in their ability to match American industrial output. The recovery began in mid-March 1945, as Japanese naval personnel secured the downed aircraft off Ishigaki. Despite saltwater immersion and combat damage, substantial portions remained intact. The massive bomb bay structure showed minimal deformation. The right radial engine, though seized, retained its basic integrity. Most importantly, the aircraft's construction methods remained clearly visible for technical analysis. Word reached the Yokosuka Naval Air Technical Arsenal south of Tokyo that an intact example of America's primary carrier-based torpedo bomber had been recovered. Yokosuka represented the pinnacle of Japanese aeronautical engineering capability. Engineers there had examined captured Allied aircraft throughout the war, recovering examples from battlefields across the Pacific. But most captures involved damaged aircraft or incomplete wrecks salvaged from crash sites. An operational TBM Avenger, even one damaged in combat, represented an extraordinary intelligence opportunity. The aircraft that Japanese salvage crews recovered in March 1945 was a TBM-3, the most advanced production variant. Built by Eastern Aircraft Division, General Motors' wartime subsidiary, it incorporated refinements developed through 3 years of combat experience. The -3 model featured strengthened structure, improved armor protection, and provision for external ordnance that earlier variants lacked. Japanese specialists began with systematic photography and measurement. Every dimension was recorded. Wingspan of 40 feet 11.7 inches, length of 33 feet 4 inches, height of 16 feet 2.3 inches with wings folded for carrier storage. The overall size immediately drew attention. This single-engine aircraft was enormous, heavier than many Japanese twin-engine bombers. The empty weight exceeded 4,580 kilograms. Combat-loaded, it approached 7,200 kilograms. Japanese engineers understood that such weight required exceptional power and structural strength. More troubling was the realization that American industry could manufacture aircraft of this size and complexity for single-seat carrier operations. The examination revealed construction methods that technical personnel found both impressive and disturbing. The bomb bay structure dominated the aircraft's midsection, a cavity large enough to accommodate a Mark 13 torpedo measuring over 13 feet in length and weighing 907 kilograms. The design allowed for alternative payloads: 1 2,000-pound bomb, 4 500-pound bombs, or up to 12 100-pound bombs. This versatility represented sophisticated systems integration. Japanese torpedo bombers carried fixed payloads. The Nakajima B-5N Kate, Japan's primary carrier-based torpedo bomber since 1938, accommodated one 800-kilogram torpedo or equivalent bomb load, but changing between configurations required significant modification. The Avenger's bomb bay accepted different payloads without alteration. Shackles and release mechanisms adjusted automatically. Armament specialists could reconfigure the aircraft between missions using standard ground equipment. This flexibility multiplied the aircraft's tactical value. The same bomber could strike surface ships with torpedoes, attack land targets with high-explosive bombs, or lay mines in enemy harbors. Mission planners possessed options Japanese commanders could not match. Disassembly of the bomb bay structure revealed construction methods that astonished Japanese technical teams. The bay doors, control mechanisms, and structural supports showed remarkable precision manufacturing. Load-bearing members were machined forgings of exceptional quality. American metallurgy had produced aluminum alloy components with strength characteristics. Japanese facilities struggled to achieve consistently. The bay's interior dimensions and structural design indicated sophisticated engineering analysis. Every component served multiple functions. Structural members provided strength while routing hydraulic lines and electrical cables. Door mechanisms incorporated fail-safe features preventing accidental release. The entire assembly demonstrated systematic design philosophy, where every element contributed to overall capability while maintaining manufacturing efficiency. Attention turned to the Wright R-2600 twin cyclone engine. This 14-cylinder two-row radial produced 1,700 horsepower. Japanese engineers had encountered this engine type before in captured aircraft, but never had they possessed an example in sufficiently good condition for thorough analysis despite saltwater damage. Over 50,000 R-2600 engines had been manufactured at plants in Paterson, New Jersey and Cincinnati, Ohio. This production volume exceeded total Japanese radial engine manufacturing across all types. The scale of American engine production represented industrial capability that seemed almost incomprehensible to Japanese specialists examining the captured bomber. Engineers carefully documented the engine's construction. Bore measured 6.125 inches, stroke 6.3125 inches, displacement 2,603 cubic inches, maximum rotation 2,600 revolutions per minute, weight 1,980 pounds. These specifications indicated an engine designed for sustained high-power operation. The cylinder construction revealed manufacturing precision Japanese factories could not consistently replicate. Each cylinder was a precisely machined casting with integral cooling fins, tolerances measured in thousandths of an inch. Surface finishes showed consistent quality across all 14 cylinders. This uniformity indicated automated manufacturing processes with rigorous quality control. The supercharger system particularly impressed Japanese technical staff. The two-speed single-stage gear-driven supercharger maintained power output across varying altitudes. Japanese engine designers understood supercharger theory, but manufacturing reliable high-speed rotating machinery required metallurgy, precision machining, and quality control that Japanese industry increasingly lacked as the war progressed. Crankshaft examination provided further evidence of American manufacturing sophistication. The massive forging showed no visible flaws. Bearing surfaces exhibited mirror-smooth finishes. Balance weights were precisely positioned. This single component represented dozens of manufacturing operations, each requiring exacting standards. The conclusion was inescapable. American factories possessed machine tools, skilled operators, and quality control systems that Japanese industry could not match. The propeller installation demonstrated similar engineering maturity. A three-bladed Hamilton standard constant-speed propeller automatically adjusted pitch to maintain optimal engine speed under varying flight conditions. The hydraulic control system incorporated in the propeller hub showed sophisticated mechanical design. Dozens of precisely machined components worked in concert to regulate blade angle through complex flight regimes. Japanese engineers examined the hydraulic control mechanisms throughout the aircraft. Actuators for landing gear, wing folding, and bomb bay doors all showed standardized construction. Fittings used consistent thread standards. Lines connected with identical couplings throughout the aircraft. Any hydraulic component could be removed and replaced without modification. This interchangeability simplified maintenance and reduced downtime. The electrical system revealed even more sophisticated standardization. Every wire connection used machine-crimped terminals rather than hand-soldered joints. Wire gauges followed consistent standards throughout the aircraft. Circuit breakers, switches, and instruments appeared to be modular units designed for quick replacement. Japanese aircraft electrical systems typically required skilled electricians who could solder connections, adjust contacts, and troubleshoot complex wiring. The Avenger's electrical system was designed so mechanics with basic training could replace entire assemblies using simple tools. The cockpit layout provided insight into American design philosophy. The Avenger accommodated 3 crew members: pilot, radio operator bombardier, and turret gunner. The pilot's position featured a comprehensive instrument panel, engine gauges, flight instruments, radio controls, weapons systems, all organized logically for single pilot operation. The sophistication of the cockpit arrangement demonstrated advanced systems integration. What Japanese aviation experts found most remarkable was simplicity despite complexity. The Avenger incorporated advanced systems, autopilot capability, radar in later variants, comprehensive radio equipment, yet cockpit controls remained manageable for a single pilot. American engineers had perfected subsystems to such a degree that minimal pilot input was required. This contrasted sharply with Japanese multi-engine bombers, where complex systems demanded constant attention from multiple crew members. The defensive armament installation revealed American firepower philosophy. Original armament included one forward-firing .30 caliber machine gun in the nose, later replaced by 2 wing-mounted .50 caliber guns. One offset .50 caliber gun in a power-operated, rear-facing turret, and a single .30 caliber hand-fired machine gun mounted ventrally. Later variants upgraded all defensive weapons to .50 caliber for increased effectiveness. The power turret particularly interested Japanese gunnery specialists. American industry had perfected electrically operated gun turrets that tracked targets smoothly while maintaining firing stability. The turret's electric motors, gear trains, and control systems represented precision manufacturing across dozens of components. Japanese attempts to develop comparable turrets had largely failed due to manufacturing limitations and electrical system reliability issues. Examination of the aircraft's structural design revealed fundamental differences in engineering philosophy. The Avenger used all-metal construction with stressed skin design. The fuselage was a semi-monocoque structure where aluminum skin panels carried aerodynamic loads, while internal frames and stringers provided shape and reinforcement. This construction method required sophisticated understanding of structural mechanics and advanced manufacturing capability. Wing construction showed similar sophistication. The main spar was a massive I-beam forging running the wing's length, ribs stamped from an aluminum sheet attached at regular intervals, forming the wing's shape. Skin panels riveted to ribs and spars completed the structure, with the metal skin itself carrying substantial aerodynamic loads. This stressed skin construction saved weight compared to older fabric-covered designs while providing superior strength. Japanese engineers noted that despite the Avenger's advanced structure, portions of outer wing surfaces and all control surfaces used fabric covering. This seemed contradictory until further analysis revealed deliberate design optimization. The fabric covering reduced weight, where structural loads were minimal. It simplified repair in forward areas where facilities for metalwork might be unavailable. and it provided adequate strength and weatherproofing while saving aluminum for critical structural components. This represented a mature understanding of resource allocation for optimal performance. The wing folding mechanism drew particular attention. Grumman had designed the Avenger to use the company's patented stow-wing compound angle wing folding system. This mechanism allowed wings to fold upward and slightly aft, minimizing the aircraft's footprint on carrier decks and in hangar spaces. The folding mechanism incorporated hydraulic actuators, mechanical locks, and electrical interlocks, ensuring safe operation. The entire system demonstrated sophisticated mechanical engineering. Japanese carriers used aircraft with folding wings, but mechanisms were often manually operated and required multiple deck crew members. The Avenger's powered wing fold reduced manpower requirements and accelerated deck operations. This seemingly minor feature multiplied carrier effectiveness by reducing aircraft handling time. More aircraft could be launched and recovered in a given period. Deck space could be used more efficiently. These advantages compounded across an air group, significantly increasing carrier striking power. The landing gear installation revealed similar attention to operational efficiency. Main gear struts retracted into wing wells, fully enclosed when retracted. The tail wheel also retracted completely. This streamlining reduced drag and improved performance. But more importantly, it demonstrated American willingness to accept mechanical complexity for operational advantage. Japanese aircraft often used fixed landing gear or partially exposed retractable systems to reduce weight and simplify maintenance. The Avenger's fully retractable gear required additional hydraulic systems, well structures, and door mechanisms. Each component added weight and potential maintenance requirements. Yet American designers accepted this complexity because performance benefits justified the cost. This calculation reflected confidence in manufacturing capability and maintenance support that Japanese forces increasingly lacked. Fuel capacity analysis provided sobering insights into American operational planning. The Avenger carried 330 US gallons in integral wing tanks, plus two 58-gallon droppable slipper tanks under outer wings. Total internal and external fuel exceeded 440 gallons. This provided a combat radius exceeding 500 miles under typical conditions. Japanese torpedo bombers carried less fuel and operated at shorter ranges. More revealing was provision for a jettisonable bomb bay ferry tank. A 275-gallon auxiliary tank could be installed in the bomb bay for ferry flights, dramatically extending range when combat payload was not required. This flexibility indicated systematic thinking about logistics and aircraft deployment. American planners anticipated the need to reposition assets across vast Pacific distances. They designed aircraft accordingly, incorporating features that simplified forward deployment and reduced dependence on specialized support. The armor protection installation demonstrated American commitment to crew survivability. 150 pounds of armor plate protected the cockpit and critical systems, plus a 1.5-inch thick bullet-resistant glass panel behind the windscreen. This substantial protection represented engineering philosophy fundamentally different from Japanese practice. Japanese aircraft designers had largely abandoned heavy armor in favor of lighter weight and improved maneuverability. The Zero's early success seemed to validate this approach. Superior agility allowed skilled pilots to avoid enemy fire while pressing home attacks. But as American fighters grew more powerful and better armed, the lack of protection became fatal. Japanese pilots died in aircraft that burned from single hits. The Avenger demonstrated that proper engineering could incorporate substantial protective armor without sacrificing performance. The massive power of the R-2600 engine compensated for armor weight. American designers accepted reduced maneuverability because they understood that survivability mattered more than dogfighting capability in a torpedo bomber. Crew protection allowed experienced aircrew to survive combat and apply their skills in future missions. This long-term thinking about force preservation contrasted with Japanese acceptance of high attrition rates. Examination of the self-sealing fuel tanks revealed another dimension of American technological superiority. The tanks incorporated multiple layers of rubber compounds that swelled when punctured by projectiles, sealing holes, and preventing catastrophic fuel loss. This technology required sophisticated materials, science, and precision manufacturing. Japanese attempts to develop comparable systems had produced inconsistent results. Sealing compounds often failed under combat conditions or degraded over time in tropical climates. The Avenger's fuel system worked. Japanese technical reports documented numerous instances where American aircraft survived hits that would have destroyed Japanese bombers. The self-sealing tanks, combined with armor protection and robust structural design, created aircraft that could absorb tremendous battle damage and return crews safely. This capability multiplied American combat effectiveness by preserving trained personnel and reducing aircraft losses. By April 1945, Japanese engineers had completed their detailed examination. Technical reports documented every aspect of the captured Avenger's design, construction, and capabilities. These reports circulated among aviation specialists, reaching design bureaus and military planners. The conclusions could not be avoided. In nearly every category examined, American technology exceeded Japanese capabilities. The gap was not small or easily closed. It represented years of industrial development, massive investments in research and tooling, sophisticated supply chains, and resources Japan simply did not possess. The Avenger was not superior because of revolutionary aerodynamic design or exotic materials. It was superior because American industry could manufacture complex aircraft incorporating advanced systems, then produce them in quantities that overwhelmed Japanese defenses through sheer numbers. Total Avenger production reached 9,836 aircraft. Grumman manufactured 2,290 TBFs before concentrating on fighter production. General Motors' Eastern Aircraft Division produced 7,546 TBMs. This production volume exceeded Japan's total output of all carrier-based torpedo bombers across the entire war. The mathematics proved devastating when Japanese analysts calculated production rates. If American factories could build Avengers with such precision and consistency, they could build them rapidly. If they could build heavy torpedo bombers this quickly, their production of fighters and other aircraft must be proportionally greater. Japan had entered a war of industrial attrition against an opponent with 10 or 20 times its manufacturing capacity. What made these conclusions particularly sobering was the context in which they were reached. By April 1945, Japan faced imminent defeat. American B-29 superfortresses appeared over Japan in formations that Japanese defenses could not stop. Each raid destroyed production capacity that could not be replaced. Aircraft factories at Musashino, Nagoya, and Kawasaki suffered severe damage from precision bombing. The strategic bombing campaign against Japan's aircraft industry had intensified throughout 1944 and early 1945. Every raid reduced Japanese manufacturing capability. Skilled workers died in bombing raids or were diverted to military service. Raw materials grew scarce as shipping lanes closed. Quality control deteriorated as pressure mounted to increase production despite shrinking resources. The captured Avenger represented everything Japanese industry could no longer achieve: consistent quality across thousands of precisely manufactured components, interchangeable parts enabling rapid field maintenance, advanced systems integration requiring sophisticated engineering and manufacturing coordination, abundant resources allowing designers to prioritize performance over material economy. Japanese aviation specialists who examined the Avenger understood that their defeat was inevitable. The aircraft before them was not an isolated example of American capability. It was representative of systematic industrial superiority across every dimension of manufacturing. For every Avenger shot down, American factories produced replacements faster than Japanese industry could replace lost aircraft of any type. The payload capacity differential particularly highlighted strategic disparities. The Avenger could carry one Mark 13 torpedo weighing 907 kilograms or up to 2,000 pounds of bombs. The Nakajima B-5N Kate carried one 800-kilogram torpedo or equivalent bomb load. The American aircraft delivered more ordnance per sortie, but the real advantage lay in total payload delivery capability across entire air groups. American carriers typically embarked 15 to 20 Avengers per squadron, with multiple squadrons in an air group. These aircraft could deliver devastating weight of ordnance in coordinated strikes. Japanese carriers, by 1945, struggled to maintain operational aircraft of any type. Shortages of planes, trained pilots, and spare parts reduced striking power to fractions of theoretical strength. The Avenger's versatility multiplied this advantage. The same aircraft that delivered torpedoes against surface ships could drop bombs on land targets, lay mines in harbors, conduct anti-submarine patrols, or perform reconnaissance missions. American air group commanders possessed tactical flexibility Japanese counterparts could not match. Mission planning could adapt to intelligence updates, changing weather, or emerging opportunities. Japanese torpedo bombers served single roles. The B-5N Kate operated as a torpedo bomber or level bomber, but lacked provisions for other missions. Reconfiguration required extensive modification. This specialization made sense when resources were abundant and multiple aircraft types could be deployed. But as losses mounted and production declined, inflexibility became crippling. Aircraft optimized for naval strikes sat idle when land targets demanded attention. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. The examination of the captured Avenger occurred as Japan's carrier aviation effectively ceased to exist. The Battle of the Philippine Sea, in June 1944, had cost Japan hundreds of aircraft and irreplaceable trained pilots. The Battle of Leyte Gulf in October 1944 destroyed remaining carrier striking power. By early 1945, Japanese carriers sat in port, unable to operate due to lack of aircraft, fuel, or trained crews. American carriers, meanwhile, operated with impunity off Japan's coast. Task forces launched hundreds of aircraft daily against targets throughout the home islands. The disparity in operational capability reflected cumulative advantages in manufacturing, logistics, training, and technological sophistication. The Avenger exemplified these advantages, rugged enough to operate from primitive forward airstrips, reliable enough to conduct extended missions over hostile territory, maintainable enough to sustain high operational tempo with limited specialized support. Technical reports from Japanese engineers examining the captured Avenger noted manufacturing techniques that seemed almost impossible to replicate. Rivet installation showed consistency measured in 10,000ths of an inch. Welding quality was uniform across hundreds of joints. Machining tolerances on engine components exceeded Japanese factory capabilities. Every aspect of construction demonstrated precision manufacturing at scale. This precision enabled the interchangeability that so impressed Japanese analysts. Any part manufactured to specification would fit any aircraft of the same model without adjustment. Field maintenance crews could replace major assemblies without skilled fitting work. A wing damaged beyond repair could be replaced with a spare from supply stocks. An engine could be swapped in hours rather than days. This maintainability kept American aircraft operational at rates Japanese forces could not approach. Japanese aircraft maintenance required skilled technicians who understood how to adjust and modify parts for each specific aircraft. No two Japanese aircraft were truly identical. Parts from one aircraft often needed adjustment before fitting another. Repairs in forward areas demanded expertise that became increasingly scarce as losses mounted. The American approach eliminated these limitations by ensuring precision was built into manufacturing rather than depending on craftsman's skill during assembly and maintenance. The oxygen system for the Avenger's crew demonstrated another dimension of American manufacturing depth. Precision regulators controlled flow to each crew position, automatically adjusting delivery based on altitude. In Japanese aircraft, such regulators would be assembled by highly trained specialists. The Avenger's regulators bore manufacturer stamps, indicating production by automobile parts suppliers. Companies with no prior aircraft experience could produce precision aircraft components simply by applying existing manufacturing capabilities to new products. This discovery carried profound implications. American industry possessed such depth that automotive suppliers could produce aircraft components without specialized aviation experience. The transition from peacetime consumer goods to military hardware proceeded smoothly because fundamental manufacturing capabilities transferred between applications. Japanese industry lacked this flexibility. Aircraft production depended on specialized facilities that could not easily expand or adapt. The bomb release mechanisms told a similar story. Japanese bomb racks required careful adjustment by armament specialists. Installation and calibration demanded hours of skilled work. The Avenger's bomb shackles were self-adjusting mechanical devices requiring no calibration. Ordnance crews could load weapons using standard procedures without extensive training. This simplification accelerated turnaround time between missions and reduced dependence on specialized personnel. As Japanese engineers compiled their findings through April and May of 1945, the strategic situation deteriorated catastrophically. Okinawa fell after 3 months of desperate fighting. American forces now possessed advanced bases within easy striking distance of Japan's home islands. The invasion of Japan itself appeared imminent. In this context, technical reports on the captured Avenger served not as intelligence for future victories, but as final confirmation of why defeat was inevitable. The aircraft embodied systematic American advantages across every dimension of industrial warfare: superior manufacturing precision, abundant resources, deep technical expertise, sophisticated supply chains, comprehensive quality control, training systems producing skilled crews faster than combat losses. These advantages compounded over time, creating capability gaps that no amount of courage or tactical skill could overcome. Japanese fighter pilots who had survived 3 years of combat understood this reality. They had faced Avengers in dozens of engagements. They knew the aircraft's weaknesses. It was not maneuverable. It could not dogfight effectively. A skilled Zero pilot could outturn an Avenger and position for killing shots, but shooting down one Avenger accomplished nothing when 10 more appeared the next day, and the day after that, and every day thereafter, in numbers that never diminished despite mounting victories. The captured aircraft examined at Yokosuka in spring 1945 represented a machine produced by the thousands, one aircraft among nearly 10,000 manufactured. If it was shot down, American factories had already replaced it. The pilot, if rescued, would fly again within weeks. If killed, training programs graduated replacement aviators faster than combat consumed them. Japan could win every tactical engagement and still lose the strategic war through simple arithmetic. After Japan's surrender in August 1945, American occupation forces found the captured Avenger among aircraft at Yokosuka Naval Air Arsenal. The bomber had been extensively examined but never restored to flying condition. Saltwater damage and combat hits made flight testing impractical, but the examination had served its purpose. Japanese engineers understood completely what they faced. The United States Strategic Bombing Survey conducted comprehensive examinations of Japanese war production after the surrender. American engineers toured Japanese aircraft factories, documenting production methods and assessing industrial capabilities. What they found confirmed conclusions perceptive Japanese engineers had reached through examining captured American aircraft. Japanese aircraft production relied heavily on skilled manual labor. Standardization remained limited. Interchangeable parts were more aspiration than reality across much of the industry. Subcontracting networks provided components, but quality control and dimensional consistency proved problematic. Individual fitting and adjustment were common, where American factories used precision-manufactured interchangeable parts. The survey concluded that Japanese aircraft factories had been organized appropriately for producing hundreds of aircraft. American factories had been organized for producing hundreds of thousands. No amount of determination or skill could overcome that fundamental disparity in industrial organization. The war's outcome had been determined not by courage or tactical brilliance, but by systematic industrial capability compounded over 4 years. The lessons learned from examining the captured Avenger survived in the minds of engineers who studied it so carefully. In decades following the war, Japanese industry underwent a transformation more profound than anything attempted during wartime. Engineers who had examined American aircraft brought those lessons to Japan's post-war reconstruction. They understood that matching American industrial capability required not just copying American products, but implementing American production systems. The transformation required 20 years. Japanese factories that had relied on skilled craftsmen reorganized around precision machinery and automated processes. Industries that had valued individual craftsmanship learned to value systematic efficiency. Manufacturing that had been organized as collections of skilled workers evolved into integrated production systems, producing high-quality goods through process control rather than craftsman skill. By the mid-1960s, Japanese factories were producing automobiles and electronics using automated production methods comparable to American factories. By the 1970s, Japanese manufacturers had refined those methods, developing production systems that improved on American mass production techniques. Companies like Toyota, Sony, and Honda became global leaders by combining Japanese attention to detail with systematic production methods learned through wartime examination of American equipment. The story of Japanese engineers examining the captured TBM Avenger became a case study in Japanese engineering schools. It illustrated how examining an opponent's products could reveal fundamental principles of industrial organization. It demonstrated that success required understanding not just what competitors produced, but how they produced it. The captured bomber taught that modern industrial warfare was won not by superior individual craftsmanship, but by superior production systems. The Avenger shared credit for sinking the super battleships Yamato and Musashi. On April 7, 1945, 98 Avengers flew in a 280-plane strike against Yamato. The dreadnought sank after being struck by 10 torpedoes and 5 direct bomb hits. These operations demonstrated the Avengers' effectiveness in coordinated strikes against heavily defended targets. But more importantly, they showed the American ability to mass overwhelming force through systematic industrial capability. Each Avenger represented thousands of hours of skilled labor, hundreds of precisely manufactured components, sophisticated materials, and advanced systems integration. Yet American industry produced them faster than combat could destroy them. This capability determined the war's outcome more surely than any single battle or campaign. Japanese engineers examining the captured bomber in spring 1945 understood this completely. The aircraft they dissected was not exceptional. It was representative, one example among thousands identical in every meaningful way. This consistency, this ability to produce complex machines rapidly and in quantities limited only by available resources, represented the fundamental difference between American and Japanese industrial capability. Understanding this difference came too late to change the war's outcome, but the lessons learned would transform Japanese industry in the decades that followed. The massive bomb bay that so impressed Japanese engineers was not revolutionary technology. It was systematic engineering applied to a well-defined mission requirement. American designers had identified the need for a carrier-based torpedo bomber with substantial payload capacity and versatility. They designed an aircraft meeting those requirements. Then, American industry manufactured it in quantities sufficient to equip every carrier task force with overwhelming striking power. This systematic approach, from requirement definition through design, manufacturing, and operational deployment, represented mature industrial capability. Japanese aviation had produced excellent individual aircraft designs. The Zero fighter demonstrated outstanding performance within its design parameters. The B-5N Kate had been the world's most advanced carrier-based torpedo bomber when introduced. But Japanese industry could not transition smoothly from design excellence to mass production while maintaining quality and consistency. American industry possessed this capability. The Avenger exemplified it. From initial prototype in August 1941 to combat deployment in June 1942, development proceeded rapidly. Production ramped up quickly, with multiple manufacturers producing identical aircraft from shared tooling and specifications. Quality remained consistent across thousands of aircraft produced over 3 years, and throughout production, improvements were incorporated systematically without disrupting manufacturing flow. The Avenger entered service in 1942 and first saw action during the Battle of Midway. 6 TBF 1 were present on Midway Island. 5 were shot down, and the surviving aircraft was heavily damaged. This disastrous combat debut could have ended the Avenger's career. Instead, American forces learned from the experience. Tactics were refined. Escort procedures improved. Aircraft were modified based on combat feedback. By late 1942, Avengers equipped carrier squadrons throughout the Pacific. On August 24, 1942, during the Battle of the Eastern Solomons, 24 TBF Avengers sank the Japanese light carrier Ryujo. The aircraft's effectiveness in coordinated carrier strikes vindicated the design and validated American naval aviation doctrine. Over the following 3 years, Avengers participated in every major Pacific campaign. They operated from fleet carriers and escort carriers. They flew from island bases and forward airstrips. They struck targets from the Aleutians to the Philippines. And through all these operations, the basic design proved sound. Modifications were evolutionary rather than revolutionary. The fundamental concept, a robust, powerful, versatile torpedo bomber, optimized for carrier operations, remained valid throughout the war. This longevity demonstrated mature engineering. American designers had correctly analyzed mission requirements and created an aircraft meeting those needs with margin for growth. The basic airframe and systems could accommodate improved engines, additional equipment, and increased payload without fundamental redesign. Japanese aircraft often reached performance limits quickly, requiring entirely new designs when requirements changed. The examination of the captured Avenger in spring 1945 revealed truths about manufacturing, engineering, and strategic planning that Japanese specialists had suspected but could now confirm in detail. Every aspect of the aircraft demonstrated systematic American advantages. These advantages had been apparent to perceptive observers from the war's beginning, but examining physical evidence measuring tolerances, documenting materials, analyzing construction methods removed any remaining doubt. Japan had fought a war it could not win against an opponent whose industrial capacity exceeded its own by an order of magnitude. The Avenger represented this disparity in tangible form, a single aircraft embodying manufacturing precision, material abundance, engineering sophistication, and strategic thinking about force projection that Japan could observe but not replicate. The engineers who examined the captured bomber wrote their reports knowing Japan had already lost the war. Their analysis served not to identify weaknesses for exploitation, but to document the magnitude of Japan's industrial inadequacy. These reports, carefully preserved in technical archives, would later serve a different purpose. They became evidence of what Japanese industry needed to achieve in peacetime reconstruction. The transformation of Japanese manufacturing from wartime inadequacy to post-war excellence represents one of history's most dramatic industrial turnarounds. The lessons learned examining American equipment during the war provided a roadmap for this transformation. Japanese engineers understood that matching American capability required adopting American methods, precision tooling, process control, systematic quality management, standardization enabling interchangeable parts. These principles, observed in captured American aircraft, became foundations of post-war Japanese manufacturing. The TBM Avenger examined at Yokosuka in spring 1945 no longer exists. It was likely scrapped during the chaotic post-war period when occupation authorities disposed of Japanese military equipment. But the lessons it taught survived. Engineers who measured its components, analyzed its systems, and documented its construction methods carried those insights into post-war careers, rebuilding Japanese industry. They remembered that American industrial power came not from superior materials or secret technologies, but from systematic organization of manufacturing processes. They understood that quality resulted from precision tooling and process control, rather than relying on craftsmen or skill alone. They recognized that interchangeable parts and standardization enabled rapid production and simplified maintenance. These lessons, learned through careful study of enemy equipment during wartime, became principles guiding Japan's industrial rebirth. The story that began in March 1945, with a damaged TBM Avenger ditching off Okinawa, ended decades later with Japan and America as partners in advancing manufacturing technology. The examination of that captured bomber taught Japanese engineers that their defeat was inevitable. More importantly, it taught them why. And in understanding why, they learned how to ensure that industrial inadequacy would never again limit Japan's capabilities. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now and don't forget to subscribe.